In this next video, I'd like to give an example of computing a limit at infinity of what's called a rational function, which is one polynomial divided by another polynomial. Now, we've seen before an example where we tried to use the limits behave theorem to compute a limit of two functions where we could not invoke that theorem. What's going to happen here is something a little bit similar, but I'm going to show you a good trick for learning how to take a situation where that theorem does not apply and turn it into a situation where the theorem does apply. So the example that we have up here, we have a couple of questions that it's worth just checking your understanding on. So the first is, if I take the limit of just the numerator of that rational function as x is approaching infinity, what value do I get? Similarly, I could examine the limit as x is approaching infinity of just the denominator of that rational function. And then what we want to do is ask the question, if I'm looking at the limit of the rational function as x is approaching infinity, is that equal to the individual limits divided? So think about that for one moment, and the answer is no. Because infinity is a concept and not a number. It's this concept that things are getting bigger and bigger and bigger. It isn't an actual number on which we can do arithmetic. So for example, having infinity over infinity, if you're thinking of that like 5 over 5, you want to cancel those things and say that this is equal to 1, but that sort of thing doesn't make sense because cancellation is a law that applies to numbers. It doesn't apply to concepts. And our limits behave theorem is going to indicate that in order to make this work, we need a number divided by a non-zero number. So as is, this is not something to which we can apply the limits behave theorem. However, we're going to perform a little trick on this rational function so that we can use the limits behave theorem. And it really does feel like a trick because what we do in the process of algebraically, quote-unquote, simplifying this rational function really does not make it look any simpler at all. And the trick that we want to employ here is to factor an x squared out of both the numerator and the denominator. Now, factoring an x squared out of something might sound like a strange instruction because there isn't an x squared here and there isn't an x squared here. But what we're going to do is force that x squared to be factored out of the numerator. It's real easy to take the x squared out of the 2x squared part. It's a lot harder to think about how to take the x squared away from the 4x and the 3. And what we're doing is just forcing it to be so. You can check by doing the opposite of that factoring in distributing the x squared into each term of that parenthetical value, that what you end up with is the same as the thing that you have over here. Use that same trick again in the denominator to factor an x squared out of every term in the bottom, taking it out naturally from the first term and forcing it out of the other two terms. As long as x is a number that isn't equal to 0, as we discussed on the previous page, if we have an x squared in the numerator and an x squared in the denominator, we can cancel this. That's a thing that we can do when we have non-zero values in the top and the bottom of a fraction. And canceling the x squared tells us that whenever x is not equal to 0, this rational function that we have over here is equal to this other, what appears to be a much uglier function over here on the right. So as of right now, this looks like a very strange trick. There's no real light at the end of the tunnel. It truly looks to me like we've made things worse. But have faith and carry on. Now, let's revisit those questions that we asked on the first slide about our original function. We have a thing in the numerator and a thing in the denominator. Let's separate them. Let's look at the limit as x approaches infinity of just the numerator and the limit as x approaches infinity of just the denominator. We no longer have a polynomial right here, so let's go through term by term and figure out what the individual limits of each piece are right here. Because limits behave really nicely with respect to addition and subtraction, we can just add and subtract those limits to get the whole thing. The limit as x is approaching infinity of 2 is just 2. There's no x in there. As x is approaching infinity, this middle term, the numerator is just 4, but x is getting really, really, really large. So 4 over 4 would be 1, 4 over 12 would be giving me 1/3, 4 over a billion would be giving me something really small. So as this x is getting really large, a 4 broken up into that many pieces is getting really, each piece is getting really small. And so this limit is 0. And a similar thing happens over here, the 3 over x squared. The limit as x approaches infinity of 3 over x squared is also 0. 3 over something really, really big. So altogether, this limit L is 2 minus 0 plus 0. An analogous computation will tell you that the m has a limit of 1 as x is approaching infinity. And now we're really, really happy, because now that the numerator and denominator each have limits, both of those limits are equal to numbers, and the limit of the denominator is not equal to 0, everything is picture perfect for applying our limits behave theorem. And the limit of this function as x is approaching infinity is 2 over 1, or 2. And because this weird function is exactly equivalent, other than when x is 0, to our original function, we have now computed the limit that we desired. Now I'd like to end this video with asking you to try the tricks from the previous slide again to 3 different examples. So the first example should be very similar to what was done in the previous slides, and hopefully that allows you to just test your understanding. Examples 2 and 3 are a little more challenging, but will teach you something interesting about what's generally going on here. And when we resume the next video, we'll talk about how to do this process a little bit faster and more efficiently.